actually, so, yeah, because I want to use the board,
Okay.
or more importantly, the students are going to use the board to walk us through this great pulse sequence. So,
Okay.
So can we?
Yes, so if we stop sharing on and we go to the board.
Yeah, this one.
It's the trick. You have working ones.
Okay, so just to get us warmed up from yesterday. Remember, I taught you my trick to figure out the evolution of the various interactions by using by adding and subtracting, by figuring out how each interaction evolves with time. So why don't we have volunteers to walk? So we have a pulse sequence here that's called an HSQC type element, where we have carbon magnetization, and we're now evolving over time, and we want to compute the evolution of various things of interest. So I have carbon magnetization. What are the things I'm going to care about? What are the sort of evolutions that I will care about? Chemical shifts, so we'll call that. Like that, we'll call that chemical shift. So let's take this pulse sequence.
So it's after the ENAP sequence.
So right after our index.
So it's 2IZ.
It could be IZSX, it could be IZSY, but we don't care about it. We just want to compute the evolution of the various interaction terms. So let's start with chemical shift. So what happens here for carbon chemical shift evolution? How would I write that? What's the period? What's the time evolution period?
There's no net evolution.
So what I would write is T1/2. There's a 180. So now I subtract the next period. Minus T1/2. So I get 0 evolution, right? So this is a silly pulse sequence, at least from the chemical shift standpoint. What else am I interested in besides chemical shifts? What kind of scalar coupling?
CH.
Okay, so let's make a CH scalar coupling. How does this evolve? Now,
Yeah. Plus.
what?
Minus, sir.
Why is it minus?
Because C inverted.
Because I'm waiting till the carbon, and I'm going to flip the J evolution. So I put another minus, right? Okay, so this is a spectacular pulse sequence that achieves nothing. So if let's imagine there's nothing else left. What would happen if I collected this? This is if I ran this pulse sequence, and then there's a reverse inept, what would I get?
Just proton.
What would the indirect dimension look like? What would the FID look for the indirect dimension? Is it a straight line? It's relaxed. Yeah, because when I increment T1/2, I'm increasing the time period, but I'll just have like an exponentially decaying, on resonance exponentially decaying thing, which if we did a 2D Fourier transform, we'd probably get a line in the middle of frequency 0. Right? There's no oscillatory pattern. But let's continue. What else do we have besides CH couplings? CC. Okay, so now what is the carbon-carbon couple? How does that evolve?
T1 over 2 plus,
Why are you adding?
because they both split, so minus.
Why are they both flipping?
Because it is not selective first.
So you're assuming, so let's assume this is a hard enough 180 that it hits both carbons. Then it's a double negative, so you add it there. Oh, so that's interesting. So that evolves for T1. So what will this spectrum look? So let's imagine there is a carbon-carbon coupling. What would this spectrum look like when I Fourier transform?
We will see cross-split carbons. No. It's split.
Yeah, so the one dimension is proton, because we're going to go back proton magnetization.
Yes.
Why is it? I think it's you projected.
Someone put.
No, what he did made the sigma.
Oh, I see.
Yeah.
Okay, great. So now so the proton dimension, you've got the proton spins.
Yeah.
What am I going to see the indirect dimension? The evolution is cosine pi j t1.
Yeah.
What does that look like when I Fourier transform? There's no chemical shift, right?
It's double. It's double.
Centered on,
Zero.
exactly. This is what's called J-resolve spectroscopy, where the indirect dimension is just the splitting. So it's literally just two peaks,
No chemistry.
no chemical shift information. And this is called J-resolve. I mean, this type of, nobody does this anymore because you get no chemical shift, resolution in two dimensions. But this is the thing. It's J-resolve spectroscopy. You get a J column. Okay, so now, let's quickly go through this one. So what happens here for chemical shifts? That's T1, I add the 2, because I don't have a 180. What happens to the CH coupling evolution?
Zero.
0, because of a 180 of the proton. Carbon-carbon.
T1.
So then, if I recorded this spectrum, what would I get?
Now, the chemistry level. So from the.
And obviously, Anna says that you did, what are your thoughts on this?
Is this a separate spectrum or are we all doing one sequence?
This is one pulse sequence. I mean, this is now I'm trying a different.
They're not connected.
Not connected at all. Yeah, these are separate, So here, because we allow chemical shifts to evolve, no problems for the full period. We're getting rid of CH coupling by having already of the protons. But then the CC couplings evolve. So when I Fourier transform this, what am I gonna get?
Is doublet center of the carbon.
Yeah, so I'm gonna get a regular HSQC, in which every peak is a doublet in the indirect dimension. But I'm always applying decoupling.
No, it's.
I'm always applying decoupling.
Yes.
So then I'm gonna get in phase doublets, carbon separated by the carbon-carbon split, which could be a useful experiment if you want to measure carbon-carbon RBCs, for example. And then you can do an IPOP experiment to separate the two components. Okay, what is this? So let's go through this one. So carbon chemical shifts, we focus on this one. CH couplings,
T1, sorry.
CH couplings T1 because you have two elements.
Yeah.
CC couplings. So no chemical shift evolution. But now you get two different multiplets split by the CH coupling and by the C spin. Right? So and of course, so when you are designing an experiment in order to measure splittings, you can worry about the various evolutions and just make sure you put the right selective 180s and pick and choose things correctly to ensure that you only allow those couplings that you might want to be interested in measuring. And then you can use the IPOP principle to create either we'll go over that. To measure either in phase or anti-phase ionization, so you can add and subtract and get the various components. Separate. Okay, so now we have this, oh, I'm on the screen, how do I get rid of them? Why am I on, like, how do I go
You're
back?
changing it from the.
Oh. But I want to, okay, maybe I can just do this. So, there you go, so it's, you can see it, right? So now we have,
No, the Zoom people cannot see.
Oh.
So you need to switch it.
Alternatively, you could just put them side by side.
so now, if you've noticed here in these experiments, let's say I want to measure just the CH split. None of these experiments accomplish it. Because when I have the CH splitting here, I also have the CC split. So how do I turn off the CC splitting, but only maintain the CH splitting? There's two ways of doing it. I mean, there are many different ways, but two obvious ways. Because I don't want to have a CC doublet. I want to have a nice clean CH resolved spectrum. So how would I, and I want to measure things in the indirect dimension because carbons enjoy, generally speaking, better line widths. So it's the better, the choice, like protons often will have scalar couplings to other protons or have dipole couplings to other protons so that the proton line width can be compromised. So you often want to measure RBCs from the heteronuclear by including the splittings on either the carbon or the nitrogen. Okay, but now you have homonuclear interactions that you want to get rid of. So what are two obvious ways of getting rid of carbon-carbon evolution?
You could use selective burst.
So you could turn which experiment would you do? Which experiment do you use? Because I want chemical shift, and I want CH couple.
The video.
This one.
Yeah, we need handkerchief, right?
So I need chemical shift.
Yes.
So what are you gonna do to the middle? How would you change this call sequence to allow? Because this one doesn't have any CH couplings. I want CH couplings.
I
I do not want CC couplings, and I want chemical shifts. I want this. I want this. I do not want that. None of these accomplish that.
Would it be the top of one and bottom of the other?
So this with
The carbon of that last one.
this, that would be the same as this. Huh?
Shift the.
Shift the carbon, like make this selective.
Right, so like add the pulse to the carbon.
Yeah, but okay, so if I make this selective, to who? Which carbon? There's two carbons, there's my carbon and my coupled carbon.
my carbon.
Which carbon? Your carbon? My carbon?
My carbon.
If it's my carbon, if this is my carbon and I put a selective 180 on my carbon, what's my chemical shift evolution?
You want?
So is that reasonable?
Yes.
No, we want chemical, we want chemical shift evolution. We want no CC coupling. Where's what I use? We want CH coupling evolution or chemical shift, but no CC coupling. So, but it's a good, you're in the right. So this 180 should not be on your carbon or my carbon, it should be on the coupled carbon. So you have a carbon, another carbon. This is the carbon for which I want to measure the splitting. This is the passively coupled carbon. Let's make the 180 on this carbon, like you suggested. I'm going to do a little funky looking selective pulse. Okay, so now with the selective 180, what's happening to chemical? So I'm not hitting my nucleus of interest. What is this carbon evolution?
One.
This now becomes T1. Good.
But zero.
What happens to the CH coupling?
Zero.
No,
Steel.
I'm hitting the carbon and the proton. I'm hitting these two with simultaneous 180.
No, but yours.
The selective pulses on the.
Oh, I'm hitting the other guy. Sorry, you're right. I'm hitting the other guy. So now I have decoupled the CH.
Yeah.
So this is that. So this is
Zero.
Let's just remove the proton pi.
Oh, let's finish this one. Okay. And then what happened to the CC couplet? Okay, so you almost got there. It's here because you're hitting one carbon and not the other. When you have a scalar coupling between two nuclei, if you hit one of them with a 180, you refocus the J coupling evolution. So it basically reverses time. So what happens at this end, you subtract from that end, and it goes away. If I hit one of them 180 or the other one 180, I achieve it. But if I hit both 180, I flip both, and now it's back to positive. It's like two negatives creates a positive.
So you're supposed to be non-selective?
So here, I would like to get rid of carbons, carbon-carbon evolution. So this carbon, this pulse hits only one of them. So therefore it gets rid of the J coupling, it refocuses the J coupling, and this would be zero. So if I hit, if two people are coupled, and I hit one of them with 180, the J coupling will be zero evolution over that period. It's limited.
For both of them or just that one?
For that, well, for both of them. If you're looking at the other one, it would be the same thing. So if I look at him and I give you a 180, coupling is gone. If I look at you and I give him 180, coupling is gone. If I look at both of you and I do nothing, your coupling is active. If I look at both of you and I give both of you 180s, the coupling is active. Because I'm flipping you both. Okay, so here we've accomplished a little bit. This is kind of an interesting experiment because you just have chemical shift evolution. But it's a regular HS, it's a decouple, it's a wonderfully decoupled HSQC, right? But we want the we want the CH back. So what was your suggestion?
Remove the proton pi.
So let's remove the proton. 180. Now you're hitting the passive carbon with the 180, getting rid of carbon-carbon coupling, but you do not affect the CH.
So it's the same as the first one, except you're on the other carbon?
Yes. Yeah. Exactly. All right, so this literally would work, and this would absolutely work in a real experiment. This is what you would achieve. Now the problem with this is that what if I have two carbons that I have to deal with? Now I have to selectively hit two carbons, which
It's really hard.
can get harder and harder. So you can always construct, and there probably are other schemes that we could just think about. But here's one way to get that CH split. There's another one, which to get rid of homonuclear carbon-carbon. Is there a nuisance, by the way, especially in the gases? Maybe you probably still got it. Although you guys have carbonyls which are nicely separated, you can nicely hit them with selective 180, right? Sugars in nucleic acids, they're all like within 20 ppm. So the ability to effect selective 180s is a bit harder. So for us, it's a serious. Well, C alpha and C beta, what's the difference there?
50, 30 to 40.
Oh, so you guys see you put the animals okay, so the other way of doing it is look at that.
Yeah.
Is to do what's called to have a constant time. So let's and so now before we go there, before we go to this pulse sequence, let's think about the constant time step. I'm going to try to draw it and add it to this. I'm going to erase this. Okay, so
the problem of this, we cannot.
let's do the board. Okay, thanks, Eldon. Just a board. So let's think about this in the following way. We want to get rid of carbon-carbon evolution. Or, more specifically, we want there to be minimal carbon-carbon evolution as a function of T1. The only way a splitting manifests is if you allow that J coupling to evolve as a function of T1, following Fourier transformation of a cosine or a sine function, and it's modulated by either cosine pi JT1 or sine pi JT1. When you Fourier transform that signal, you're going to end up with a split. So as long as it's not evolving as a function of little t1, the thing that we're incrementing, one can get rid of such complex. Now let's imagine we come up with a difference. We decide, you know what we're going to do? We're going to have a constant time period. We're going to call that constant time period 2 delta. Delta is a delay which we can choose. It's under our control. And then, so I am committed to this delay for the indirect emission. I am not allowed in the normal HSQC experiment. You kind of grow time over time. right? Just at a longer time period. But in NMR, you can control time with refocusing pulses. So let's just now say we are stuck in a universe where we have a constant time. You don't get to increase it. How could I possibly get a signal? Let's just do chemical shift. How would you design an experiment by which you could still get a signal that's modulated by, for example, cosine omega t1? You're not allowed to increase the time. Time is fixed. But you're allowed to move pulses. So take this 180 and shift it to the left or to the right.
Either way.
Let's go left. Okay, so let's start shifting it to the left. Okay, so then shifting it to the left means that as more time, as I increment, it's moving more and more to the left. So what's the mathematical term I should write? So let's say I'm going to divide this is 2 delta. Let's put it in the middle of the meeting. Yeah. So then the 2 half periods are each delta. So in your perspective of moving it to the left, what would I mathematically call this? It's not delta because it's changed because it's moving closer and closer. So delta minus T1, T1 starting. Delta minus T1 over 2. Let's just half it here. So what would be the right side?
Plus T1 over there.
It has to, because the sum better be 2 delta. I told you that's your time allocation, right? So now you're doing an experiment, you're like, I'm going to keep it constant, and I'm just going to vary the pulse. Okay, so let's see what happens in this hypothetical experiment. What is the chemical shift evolution? Again, the trick that I taught you. What do you do at the beginning? You start, just write down the time. What's the time from the left side?
Delta minus T1 over 2.
Then what do I do to the next side? It's a 180. It's a hard 180. So what happens to the next side? Minus 2. Okay. The delta cancels, and I get minus T1. The fact that it's minus just means you're going to end up with negative frequency.
Wait, why is it minus delta minus T1? That was plus T1.
Minus.
Because when you put the 180 on the carbon nucleus that's active for the chemical shift, the 180 reverses time, so to speak. So you always subtract the subsequent period.
Okay, but isn't that period, subsequent period like the one thing, so you'd be minusing?
So I'm minusing this whole thing. So I'm minusing delta and minusing T1 over 2. So this is plus. So this period is called delta minus T1 over 2. And then I'm going to put a 180, which means I have to subtract the subsequent period. So minus delta and minus 2. So I'm just subtracting this quantity.
It's just negative. Yeah.
Just this minus that because of the 180 there. And when you do that, you're going to put minus T1. And so your chemical shift has evolved as, let's say, cosine omega T. So you've got you have generated chemical shift here, which is wonderful. All right, but now let's not worry about C. We'll come back to CH later. Let's do carbon-carbon, which are, remember the thing that we want to worry about. And let's say this is a hard 180 that hits both. What's the carbon-carbon image?
Delta minus T1 over 2. Plus.
Because the 180 is hitting both carbons, remember or many carbons, Then I'm going to add another delta plus T1 over 2, which is 2 delta. So carbon-carbon coupling has evolved. But for a fixed period, delta, not T1, there's no little t. There's no, as I move the pulse to the left, as you suggested, I am not generating a signal that's modulated by, where the J coupling is modulated by little T1. I've gotten rid of it. Is life perfect? Why isn't it perfect?
Well, it will take away signal, depending on what the magnitude of that J coupling is, how big the.
Right, so I'm still evolving the scalar coupling. So I will get something like a term like cosine to do some pi J, pi J delta, right?
Hi, J.
Where's my J? Oh. Cosine pi J 2 delta. So this signal, this function is, my signal is being multiplied by this function. What happens when I multiply my signal, my product operator, by a constant number that varies from 1 to 0? I mean, you can account for it, but what does it mean when I subtract my product operators by a constant? Let's say this is 0. What's my signal gonna be? Okay, so that's not good. Presumably 0 is bad. What would be a better thing for this term to be? Because it can be anything within the range of whatever the, this pi j2, it could be, the cosine of a function can be anything between 0 and 1, right? So ideally it would be 1.
Yeah.
So in order for this to be 1, how do I make this 1?
Make it
Make 2 delta, like, under what conditions? What multiples of what pi gives the cosine? Multiples of 4j, 1 over 4j.
Yeah.
So delta has to be set in such a way that I get j over 4. So delta has to be, okay, so how do I set, so what multiples of pi? Sorry, what multiples of pi gives me 1?
cosine.
Half of pi, full pi, even multiple. So pi, 2 pi.
2 pi.
Let's go for pi.
Yeah, sure.
Let's go for pi.
Yeah.
Yeah,
So if I want this to be pi, what do I have to set delta to?
2J.
One
1 over 2.
1 over 2j. So if delta is 1 over 2j, then the 2j's cancel. I get cosine pi. I get 1. So my signal is intact. Right? Brilliant. Right? Now, what would I want delta to be? Long or short? Well, because I have options. I mean, do I want a long delta or a short delta?
Better keep it long.
You want a long delta? Why do you want a long delta? No, so when we said, this could be pi, but it could have also been 2 pi. Right? That also would work. In which case, the delta would be twice as long. Right? So I could keep making delta longer and longer and longer. And so the question of how long you want it to be dictates ultimately how much chemical shift evolution. So within this narrow range of delta, you can keep decrementing, but at some point you hit the wall. And as long as you're happy that that's enough chemical shift evolution to resolve your peaks, you might be satisfied. Or you might come back and say, no, that's not enough. I need a larger delta. But all along this, let's go back to the simple case that we set it to pi. And we get a number of 1, we get a nice signal. Is my signal intact? Truly, I'm not losing anything from delta. So it sounds like I just coupling evolution is 1. What's happening during this experiment?
Relaxation.
It's relaxation, right? Your signal is the signal that comes out of. So in this experiment, every time you collect the signal, the magnetization, the T2 has been operating for a period of 2 delta. During 2 delta, relaxation has occurred. So the signal at the end here, when you have a T1, you start increasing the time. Very short times, there's hardly any relaxation. And then you grow the signal, and now it's getting burdened by relaxation. Here, even the first point when T1 is 0, you're still allowed, even though I'm refocusing everything, the magnetization is evolving for the period 2 delta, so you get a big hit on signal. It's not for free. So nothing is for free, right? But if you have a sample that's reasonably concentrated and you have the luxury of losing a little bit of signal, you can avoid losing signal from J coupling evolution. But also under the assumption again that what's true about all carbon-carbon J couplings, because I have a bunch of spins, bunch of I have a bunch of carbons, not one, but I have 20 different guanine residues, with all of which, each of which has a different carbon. And a different carbon-carbon couple. What's the assumption that we're making here? This will only work if all of them have the same J couple.
Yeah.
Which is roughly true. So to the extent that you deviate 55 hertz, 54 hertz, that's gonna have a negligible effect on the angle that we end up here. And that works pretty well for solution NMR. Now, if you have huge dipole couplings contributions, then the J's will be different potentially, right? Some will have a big dipole contribution, others will not. So, but generally speaking, this works well. So this is, now let's go to CH couplings. So your experiment is doing good. You've got chemical superevolution, you've got rid of carbon-carbon couplings. What's happening to the CH coupling evolution in this experiment?
Delta.
So it goes delta minus 2/2
Minus.
minus delta minus 2.
Yeah.
So,
Minus 2.
so you've got yourself some CH splitting, and you've got rid of carbon-carbon. You're happy. Because remember, that was the goal that we wanted to accomplish. Here we accomplish that by having a selective 180 on the carbon, on the other carbon. And you wind up with a spectrum in which you only had CH splittings, no carbon-carbon couplings. Here, you accomplish the same thing. You got rid of the CC couplings and you retain the CH couplings. So this experiment would be beautiful if you wanted to focus on the CH couplings. Now you could play tricks and say, well, what if you wanted to get rid of the CH and activate this? Oh, this is not the way to activate the CC. But I think some of the other experiments we did, this gets rid of the CH and activates this. If you wanted to measure a CC coupling. So the constant time experiment is another widely used element in many of the pulse sequences that we use to measure, especially carbon, especially when we want to get rid of carbon-carbon couplings. It's a common use, again, it depends on our trade-offs. Because as I said, there's a lot of relaxation during that gift. Now, this amazing sequence,
You want to change?
yeah, but I need the boards at the same time.
Really? Okay.
So let's walk through what this sequence does. So, oh, sure, yeah.
So, I mean, when I'm shifting the pulse, so if my delta is greater than T1, so for a certain period of time, it is not refocused.
It's all right.
It's not refocused.
Well, it will evolve exactly like this. So you increment T1, you're like T1 is equal to 0. T1 is equal to depending on your spectral width. You increment T1. So you go into the spectrometer, you set your spectral width, you tell it how many increments. What the hell is that called in Brooker? ND? It's still a variant. Is it called ND in Brooker? Like there are two more places like ND. So yeah, you go in and you set up so that determines the dwell time. So every time you're incrementing T1, there's a new value of T1. And that new value of T1, when you're recording a particular experiment with a particular T1 value, the evolutions will be given by this. Yes, every time. And so, but depending on the point you're measuring, the value of T1 will be different, right? There will constantly increase in time. I think what you're saying is at some point, you can't let if T1 grows beyond that, then of course you're going to come out of this floor. And your program would stop it. You would never let it go further than that. Yep. So there's a limit to how long T1 can be. Because this data gets maximum 0. So 202, the maximum value we can assume is done. After that, you're running into problems. Because you're essentially moving the pulse towards the inactive. So, was that your question or?
That's the difference.
Alright, so let's run through it. Let's say T1 equals to 0. My pulse is here, and nothing evolves except for the J couples. But we set the delta to be 1/2J, so we get no J coupling evolution. The intensity is 1, everything is good. Next experiment, I set T1 to be 0.1 millisecond, 0.1 millisecond, or whatever. Now, during that element, my chemical shift will, when I record the signal, there will be a cosine modulation of the chemical shift by a period of 0.1 milliseconds. The J coupling will involve 0.1 milliseconds, and this thing continues to go. And then I keep incrementing T1, and then I'm collecting a signal that's being modulated by the evolutions of the carbon and the carbon proton, but not the carbon. Just like as in a normal HSC. You know, normally that's what so that's the beauty of this scheme, is that the output of any HSQC is simply something that's modulated by T1, right? It's either chemical shifts or J couplings. And depending on what you design in your experiment and what terms you allow to evolve, your spectrum will differ. But you can achieve the same mathematical signal by playing pulse sequence games where you move pulses in rather than move time. Right, good. Is it just, are you just interested in, are you just amazed by how great the cards are cut? Or are you, or is that good confusion or bad confusion?
So suppose my pulse is now at a 1/3 position,
Like here.
then my spin is only up till the 1/3
Yeah.
equal period. But beyond that, also there is no refocusing, right? So
I mean, that's the effective.
Right, there is no refocusing, that's why it's T1.
Yeah.
You're right, there's lesser refocusing. So you've just made a decision to increase the value of T1, because it's moved really close. And because of the fact that you're not refocusing fully,
Yes, correct.
there will be a lot of evolution by an amount T1. But remember, the value of T1 is changing. T1 is a variable of time.
So for regular HSQC, the T1 interferogram is this M-damp oscillation. And just Fourier transform that T2, then I get that. But for this experiment, it will be like the.
You're absolutely right, so it's not damped,
Yeah,
because every point is the same. And one of the advantages of that is you can do linear prediction. So there's something called linear prediction, where you can take a given, because of the fact that the sinusoid looks, it's like, hey, this looks like pretty regular. You can do a mathematical manipulation to increase the number of points artificially because of the limitations imposed by delta. This is not a perfect scheme, but you can do this to increase artificially the number of points in a way to kind of combat the artifacts of Fourier transformation. This is all just, it's like zero pulling, you know, it's just the need to go to the frequency domain.
right.
So it's again, there's no way you're gaining anything other than defeating the artifacts that come out of Fourier transformation. So, all right, this is good. Okay, so then this amazing sequence, and I say it's amazing because I coded it as a value student. It's actually the only sequence I can actually publish. But anyways, so let's ask, what does this do? Okay, so now we'll play the game, but our starting point is here. And we're gonna go all the way to here. Okay. So. All right, so once again, if I have carbon chemical shifts, it doesn't matter what it is, right? Don't face it, IZ, SZ, or whatever, we don't care, it's something. So here, chemical shifts, again, I have a delta period, delta minus T1 over 2. Is that what it says?
Yeah.
Then I have, is that a 180? I think that's 180.
Yeah, sure.
So what do I do to this term now? I have a 180 on the carbon, so what happens, what do I do to this term? Flip it, so what is it, minus?
Yeah. Plus Q1 is over 2.
So this looks a lot like this, right, of your experiment. So far. Have you noticed? So this first half is identical to your experiment. Right? So we can just fill in the numbers, right? So that's gonna give me minus T1, right? As it did before. carbon is gonna be 2 delta, because it's gonna go for this plus that.
Then,
No, that,
that's not like.
Oh, delta, because it's more common, because there's the other, so this pulse sequence is divided into 2 halves. So there's one delta on the left and there's one delta on. So, yeah, so the first half is that 1 delta. And then the CH couplings are minus 2. Good. So all that is just like we did. And now what is going on later? Let's continue. So now there's the other half. So, well, I have a little T1/2. So chemical shifts, remember, I was in the minus, remember we flipped it? After this 180, we were flipping chemical shifts. So we said minus this, now I have to add a minus T1/2, right? So I'm gonna continue, minus T1/2. And then I have a 180 on proton. So what do I do with this term? Just continue negative, continue, because proton 180 does not affect the carbon chemical shift. The carbon is like, I'm me.
sorry, actually, should it be like this?
No, kids, I don't make mistakes. I don't make mistakes.
Okay.
Well, let's see, maybe it's wrong. Let's continue. Delta, minus, what is it, minus delta?
Minus.
It's my, like my, I'm gonna just do this, minus,
1/2.
right?
And then a 180.
So then I have a 180. So what do I do with this? Well, because now I used to be my, I go plus. All right, so what do I have?
Wait, Hashi,
Yes,
isn't it chemical evolution for sleep?
yes.
Then it doesn't flip here.
No, it doesn't flip. Did I flip it? Yeah, so
Yeah,
it's
usually.
plus, minus this, minus that.
Minus that, and
Yeah.
still minus.
Still minus that.
Sorry.
And then plus that.
Plus, yeah.
So we agree that's it, right? So then let's delete this and that. I'm a little bit scared of this. This is interesting. What's happening here? So then I have minus G1. This is.
This is delta T.
You think this is what?
There should not be, then we get that.
Okay. Let's look at this. So I think ideally we want carbons to evolve with chemical shift. So minus 2. This is not a very nice term. It's got an ugly delta in it. Are there no more deltas in there? No, right?
Isn't there be a third?
Am I missing it? Is that?
Is the
So
one on the
what
other
is
side,
that?
the 180 supposed to be delta plus 2/1/2 again?
This one here.
Yeah,
Yeah, this one is weird.
that's supposed to be delta plus.
This should be
2/1/2.
delta plus T2 probably.
Ah.
Let's make it delta plus. That was my thesis. So let's
Yeah,
do
yeah,
that.
yeah.
Okay, so, because that would be good, then we would, then these two things would cancel. But I still have the minus two. Yeah, this,
How much time is passing in between that first delta plus 2/1/2 and the second one?
so let's do
Is
this.
that just T1/2?
Let's do this. Somebody pull out a paper, because let's make sure I have the right policy. So look up Alashini and Percival. That's interesting.
Oh, this is not constant time. Then. Because if you look
It's
at
not constant time.
it
Here,
doesn't look like it. Yeah.
It gets rid of carbon compounds.
Oh.
So it is constant time for carbons.
Oh, okay.
but this is constant,
Yes,
delta, and this should be delta, right?
it should be constant, but it's not.
It's not, it looks not.
It looks, yeah, but you're gonna let you impress it, right?
Which year?
It was, it's on a sugar. Jacks.
CTC, HSTC.
Yeah, CT, yeah, but we should.
Gee, you have too many papers.
Yeah, so, it's not bad. Maybe I can use Google. No, go to PubMed.
said jacks, right?
Yeah. Yeah.
Oh, 2000, nope, that's maybe.
Yeah,
What?
oh, 1K.
Is this the dipolar coupling fish?
It's a shit, I wasn't.
And this one.
Residual dipolar coupling,
Yes.
2001?
2001.
Yes. You first thought that.
No, I'm checking out. So then, yeah, that's it.
Oh, I found it.
Um,
It is the delta.
So the pipeline my thesis. Okay, so let's see,
Your mistake.
as we see, yeah, so this is delta over two, not T one over two. Wow, this is kind
Makes
of like,
sense, makes sense.
I better go and fix my thesis. Okay, so this little T one is a delta, so let's go back here. Well, I'm not sure that's, hopefully that, we can't retract the paper, yeah. Okay, so that's delta. Is that correct?
Yes.
Yes.
Yep.
Okay, life is better. Because the minus delta over two cancels with that,
Minus 3.
and I get minus T1 again, so I get
You're nice.
minus 2T. Or am I, so there's a minus T1 here. Let's do this correctly. Let's do it correctly. So, okay, tell me what I'm supposed to write.
Minus T1 over 3.
Oh,
No,
right,
minus T1.
right here,
Right.
yeah, sorry. Yeah, so tell me what to do.
Minus T1 over 2.
Right?
Minus
Delta minus
delta
T1.
minus T1 over 2.
Like that?
Yeah.
Yeah.
Plus
And
delta over two.
plus T1 over 2.
Delta over two.
Delta over 2.
Delta over two.
Delta over 2.
Okay, so. This cancels with that. And then I have a minus T1 over two and another minus T1 over two, right?
Cancel.
What?
Oh, yeah, these cancel.
Yeah.
So I end up with just minus.
Just minus 2.
Nice.
Okay, great. Okay, so it's at that point, you can make these. Okay, see, actually, that was a trick question. Just making sure you're paying attention.
Yeah.
Okay, so let's go to C. Can we make sure we use your, is it?
I'm looking.
So we're good. So now let's do CH column. Tell me what I'm supposed to write for CH.
Delta minus T1.
So we knew that CH, this first block was always minus two.
Yeah.
So I'm gonna just write minus
Minus
two.
T1.
Now let's go to the next one.
Yeah.
Then what?
2 minus,
Minus T1 over
yeah,
two,
minus T1 over 2.
yes,
Plus,
plus.
yeah,
Do you notice the difference?
yeah.
So now we're going plus delta
Delta
minus T1 over two. Then
Minus delta over two.
minus delta over two,
Yes.
delta over two. So what's happening? Now, the delta cancels out, but I'm getting myself another minus T1 over two,
Yeah.
minus T1. So what is happening? Minus
Minus-
T1, minus T1,
Minus,
minus two T1. Okay? Let's do carbon-carbon addition. I don't know what I'm supposed to write. And those are hard 180s on the carbon.
start from delta.
Yeah, remember, yeah, we started with two delta. Oh, delta, sorry, delta, because it's one delta.
Yeah.
Then let's start for the second half. So we had this hard 180, so we're in the minus. No, it's a hard. So it's all positive.
All positive,
Yeah.
still positive.
Yes.
Plus T1 over 2.
Okay.
Plus delta minus T1 over 2. Minus.
No, not minus.
No, it's hard first. Again, hard first, so plus
Plus delta.
delta over 2.
Okay.
2 red.
So that gives me another delta. So I end up with two delta. So I retained the two delta of the previous experiment. So is carbon-carbon coupling evolving? What am I gonna see in this experiment?
we see.
Do we see carbon chemical shifts?
Yes,
Wonderful carbon chemical shifts.
yes.
When I see carbon proton splittings,
Double.
they're gonna be double,
Double.
because there's two people. So this is a coupling enhanced scheme. Will I evolve carbon-carbon? No.
No.
So I have, if I constructed a constant time coupling enhanced sequence, where I double the apparent splittings, but retain the constant time. Again, and you see the way we design the pulse sequence is divided into two different deltas. In one delta, I have chemical shift and coupling evolution. In the other delta, I have only
Only a couple.
coupling. Right? So in one delta, I say both of them apply, carbon, the chemical shift evolution and CH couplings. And in the second delta, I get rid of the chemical. How did I get rid of the chemical shift in the second period? What is it about the second period that gets rid of the chemical shifts?
The fact that it's not.
It's just a brilliant sequence. I mean, it just works out that the chemical shifts get removed, and you can analyze. You know, whenever you have an MR experiment, and you want to figure out what the spectrum is going to look like by just doing these additions and subtraction, you figure out whether something's selected or not. Of course, it can be more complex experiment from this, but the standard HSBC variant experiment can be analyzed in this way. Okay, so that was our little exercise. Now you should go and think about all kinds of cool experiments you could design to manipulate spins. Okay, so, all right, so. Okay, so I do want to spend a little bit of time on how we analyze residual dipole couplings. But before I do that, I just mentioned, so the way you measure RDCs using ordering media is you take your sample, you measure the splittings using these experiments. In the absence of phage or bicels, or in the presence of phage and bicels, and the difference in the splittings represents the dipole contribution. And remember to worry about the scalar coupling, whether it's positive or negative, and how that impacts things, right? But that's how you do alignment measurements in using alignment media. But as I mentioned, there is a way to measure magnetic field-induced RDCs. If you take a nucleic acid that's long enough and you put it in a magnetic field, it will spontaneously align. And as we discussed last time in class, the alignment level, and therefore the observed RDCs, depends quadratically on the field's strength. So you double the field, you get 4 times more alignment and 4 times greater RDCs. The problem is that what a real RDC is, the dipolar contribution is, so let's say I measured something at 600 megahertz, where it's a little aligned. And then I measure it at 900 megahertz, where it's aligned even more. That difference between 900 and 600 isn't really the dipolar contribution, because at 600, there's already some level of alignment, and therefore some degree of RDC contribution. You know, the RDC contribution is relative to scalar coupling. So put it differently, how can you measure the scalar coupling if even at 600 megahertz, your sample is spontaneously aligned? So what's the answer? Just extrapolate. So you know the dependence is B squared. So here we're plotting the observed splitting on the y-axis versus B squared. Right? And that should be a linear dependence. Right? So you measure the data at 800, you measure at 600. Notice how small these RDCs, by the way, are. Like the whole thing is, you know, 2 hertz, right? These are really, really tiny. These are actually the first things we ever measured in my lab. Me and Chizang measured these splittings. So but you can see it's pretty nice. It's a good line. You can measure them, you know, reasonably precisely. And then you extrapolate to what would be the scalar couple, what would be the splitting at 0 field. And that's your honest scalar coupling. And then you can subtract whatever splitting you measure at the highest field, because you want to get the largest amount of juice, the largest RDC, from the extrapolated value. Now, you could subtract 800 and 600, but you're getting pseudo RDCs. These are not, you're basically measuring one alignment and another alignment, and it's not a real RDC, which can be physically interpreted, because you're having an RDC contribution at a small field. Now, the reason why you can get alignment is, as I mentioned before, every little base has a magnetic susceptibility tensor, which we'll call chi, which determines that results in a degree of alignment. And normally one base alone, like benzene, would give you an RDC of about 0.1 or less than 0.1 hertz, very small. But if you have a bunch of these bases stacked on each other, all co-aligned, like you do in a nucleic acid helix, then the physical interpretation is you literally do a tensor sum. You take all the tensors, they're x, y, three-dimensional vectors, you just sum them all up across all the bases to get a macroscopic high tensor. And that is then the operative tensor. And as a result of adding up all those mini tensors, you can get a very large, in this particular case, I'm showing you an example of two domains where each domain has its own macroscopic chi tensor. And then you sum those two up to get the macroscopic one. And that's the reason why you get more alignment. Now, you might ask, well, how much is this alignment that you're getting out of magnetic alignment? So this is a plot that shows you the predicted alignment. This is all predicted data for a helix that of variable length. The optimum order is shown here as 1. So 1 is the amazing degree of alignment you get from phage or bisects. Now, normally, we're talking about 40 base pairs, and we are, let's say at 900 megahertz. This was the past. And if you're doing 40 base pairs and 90 megahertz, your alignment level is far from optimal by a factor of 10, roughly. So magnetic alignments in the old days of not having high fields and being restricted to relatively small base pairs. But what's interesting, by the way, this review was written in 2007. Kind of interesting that we have 1.2 gigahertz machines which exist today. So at 1.2 gigahertz, for a 60 base pair, if you take a 60 base pair DNA, which like we have, I think 40 base pairs in our lab. I don't think we went to 60, but it's not totally unreasonable to. But this is assuming a perfect helix. Because if you're a tRNA and your helices are sticking in different directions, your tensors are not going to sum. But if we made DNA in the lab today, which we could, so you can synthesize an oligonucleotide 60 base pairs long, 60 nucleotides. Right? So let's say you make 60 nucleotide DNA and you label one position because we can do it. Right? So to get rid of spectral crowding. Actually, this is a great experiment. We should do this experiment. So if you take and you just label the middle, you label one residue, and then you make the partner oligonucleotide, the complementary nucleotide, and then you anneal them, and you take said sample, and you send it to Ohio, to the 1.2 gigahertz NMR spectrometer. You're going to measure 20 hertz RDCs, but the problem, of course, is that you're at 1. You have to then measure it again at lower field, which we can do. We can measure on the 400. That's another advantage, by the way, of changing the field, right?
Yeah.
So then you would do another measurement at lower field, and the prediction is that you would get as much alignment as you would have gotten from the ordering medium. So it's really substantial. Now, if you have a protein that binds your DNA, now by the way, it's kind of 40 base pairs is still big, and it's going to be a rigid duplex. It's the signal is not going to be even after we site label it. It's not going to be great. And if you increase temperature, the alignment goes down. It's like the Boltzmann bias decreases. But still, it shows that if one day we have a 3 gigahertz NMR instrument, we'll be in the solid state having to worry about how do we get rid of the lateral couplings, because in solution the system is so alive, because of the magnetic alignment. It will like push us back to not back, pushes forward to solid state NMR. If that is listening. Okay, so now the thing that we measure when we measure RDCs depends on the bond vector. So remember, the quantity we're measuring is the oh my God, another typo. That's 3 cos squared theta minus 1/2. Oh, my thesis. Well, I'm just a bit of a bad mental state. Okay, so that's 3 cos squared theta minus 1/2. Wow. That angular term is what we measure, because once you factor the depth, the distance we normally assume we know, it's the bond length. And then you have the diameter ratios of it, et cetera. So we can get rid of these. What you're really measuring is this angular term. And that term is averaged over all the orientation sample. And it's actually, that number is anywhere between, it's usually 10 to the minus 5. It's a small number, 10 to the minus 4. It's just a number. And it really doesn't really have any value, because you're talking about a molecule and its overall distribution in the field. So what? How do I'm not measuring the angle relative to your molecule. Like if theta was relative, like a bond vector relative to the helix axis, you could say, oh, that's a valuable quantity to measure because it's telling me something about the structure. But that's not what I'm measuring. What I'm measuring is always the orientation of the bond vector relative to the external magnetic field. And most of the averaging is dominated by the overall reorientation of the sample. So unlike in solid state, where I think, well, that's not, well, the angular term is weird in this, because you guys get rid of the angular term and try to get the distances. But there's a challenge here. So it turns out that if I have a rigid molecule, completely rigid, and I have, let's say, a bouquet of vectors. Imagine I have a ball, which is partially aligned somehow. And there's vectors, bond vectors, going in every direction. And I take this ball, I partially align it, I measure RDCs for every bond vector, and I get a totally different value for every bond vector. If 2 bond vectors are parallel, by definition, they must have what kind of RDC? The same or different. I have 2 bond vectors in a molecule, and they're always parallel. The RDC has to be the same, because whatever angle this is doing with this field, this one being parallel will also have the same angle, right? So, but still, I have this bouquet of vectors, and I want to be able to predict. I want to be able to explain the system. It turns out, if you have something called the alignment tensor or the order tensor, it's 5 numbers. We'll go over what they are in a second. If you have those 5 numbers, you can calculate the RDC of any vector in this sphere. I don't need to know, that's all I need. And those 5 numbers actually end up being a tensor, which has an orientation and has 2, I mean, it's 3 orthogonal axes, X, Y, and Z. And each vector has each axis has a certain length. The lengths can be negative. We're living in the order. This is an order parameter world. And so when you add the 3 lengths, it's traceless, so you get 0. So out of the lengths, only 2 numbers are independent. But other than that, I have to define the orientation of this system. So how many angles do I need to define the orientation of a three-dimensional tensor relative to a parallel fragment? Why is it 2? Okay, so then theta phi tells me where this is. But what about this angle? Always for the general case, right? If it was axially symmetric, if X and Y were the same, then I just need to define theta and phi. But there's always 3 Euler angles in the most general sense that are required to define the orientation of an axially symmetric tensor relative to the chiral fragment, And as I said, each one of these vectors has a certain length. Now, it turns out that there's one unique tensor, one unique alignment tensor for every molecule. And the principal axis of the system, the longest vector, is called SZZ or AZZ. It's the Z component. And this is you can think of it as that's the vector. If you're sitting on that direction, That's the vector that enjoys the biggest RBC. And that's called the principal direction of order. It makes sense that the RBC that's enjoying the greatest value is the one that's experiencing the least variation relative to the field. It's the direction, if you were sitting on that vector and you're interested in a roller coaster ride, you'd have the most boring roller coaster ride because you'd be mostly ordered relative to the field. So that's the z direction that defines it. Once I have a z direction, by definition, orthogonal to the z there's an x and a y. The sy happens to be amongst all the options in the xy plane. If you sat on sy, that gives you the largest order. It's the one that's reorienting the least relative to the magnetic field. Okay, so SZZ is the vector that has the largest order. SYY is the direction in the xy plane that has the largest order. And then SXX, by definition, is defined as whatever is left over. So we have 3 axes, each of them has a length, and they add to 0. And now, if I have a vector in this space, let's say I have a bond vector here, calculate phi cos squared theta minus 1 over 2 for that vector. Once I know the alignment tensor, it's only a business of take this vector, project it along z, get the projection of the length along z, multiply it by the length of SZZ, plus project the vector to x, multiply it by the length of x, project to y, multiply by the length of y, and add up. And that algebraic calculation will give you the value of phi cos squared theta minus 1 over 2 for that vector. And as long as the system is rigid, all vectors are eternally rigid. So in theory, by the way, if you have 3 RBC vectors that are orthogonal, you can calculate any arbitrary RBC vector as a projected sum of the 3 vectors. You know what I mean? So you take this vector, you say, okay, I'm going to take this vector, project it along this vector, which has an RBC of 10 hertz. This is 3 hertz, you know what I mean? And you sum them up. This would work for any 3-dimensional system. Now, the one we're talking about here is the alignment tensor, which is unique because it has the largest direction of order, and then one can diagonalize this and get the analysis. So the point being that the angle alpha, the projection, once I know the alignment tensor, then a given RBC constrains the orientation of bond vectors relative to the alignment tensor. And all of us, if we are in a part of a molecule, we each share a common alignment tensor. Your alignment tensor is my alignment tensor, right? We're the same molecule, right? So therefore, the RDCs can constrain the orientation of bond vectors relative to the common alignment frame. And that's the power of the method, the measurements in terms of determining information about the orientation of bond vectors and their dynamics as well. But that's a very, yes.
So are you assuming the alignment tensor is the doubling vector?
So on average, the principal axis of the SZZ, the direction that I mentioned, the principal direction of order, is either perfectly parallel to the field, like it is in phage, or it's perfectly perpendicular to the field, like it is in the bicell system. But it is, so it doesn't have to be parallel to the field. That's for positive alignment. When SZZ is positive, then it's parallel to the field. But SZZ, if you have, so imagine I have this, and it's spinning this way relative to the field. The biggest direction of order is this direction. It's parallel to the field. Phi cos squared theta minus 1 over 2 of 0 is 1. So it's a positive alignment. But I imagine I take this and I start doing this to be annoying, you know. Now, what used to be a wonderful direction is the one that's most dynamic. And the most ordered direction is the one perpendicular to it, right? If you sat on this vector, you'd experience nothing. You'd be like, hey, you know, I'm always perpendicular to the field. So now this direction would, and it's not experiencing any averaging. This direction is always perpendicular and it's not averaging out. Everyone else is getting averaged out. So this would become the new direction of order, except the vector is perpendicular to the field. And phi cos squared theta minus 1 over 2 of that vector is minus alpha. So now the biggest direction of order, the biggest RDC is a negative RDC. In the first scenario, the biggest RDC is the positive RDC. In this new scenario, the biggest RDC is a negative RDC. And so you can have positive alignment and negative alignment depending on the system. And but still, that just changes whether what's the nature of the alignment tensor or the order tensor, but then having knowledge of the alignment tensor, you can constrain the orientation of all the vectors relative to that, whether it's positive or negative. And now, how do you get the alignment tensor? How do you determine it? That's a whole another lecture. We won't go over that, but if you can get the alignment, if you put your hands on the alignment tensor, then you can use and harness the RDCs in structure determination. All right, guys, I think I am, what are we doing? We're at 2:30. We need to, any last questions?
How do I translate information from RDCs into dynamic?
Great question. So in the situation where your molecule is undergoing dynamics, there isn't one set of projections along the alignment tensor. You now have multiple projections. So let's say I'm 50% here. That gives you one set of projections and one set of theta squared theta minus 1 over 2. And then I'm 50% there. So now I have a new set of projections and a new set. The theta squared theta that I measure will be averaged over the two. So in order to extract the dynamics information, so the dynamics information is there because you're averaged over it, So if I knew the alignment tensor and you gave me structural models, and you give me a static structure, it will fail to predict the RDCs because you're not taking into consideration the fact that the RDCs are averaged over more than one state. If on the other hand, you give me an ensemble model, and let's say you have some great force field or a great model that gives the right ensemble, then that ensemble will predict the RDCs correctly. But it's still tricky because when you change the structure, you also change the alignment tensor. So what I just told you assumes the alignment tensor is happy and fixed, and the bond vectors just change with it. But the fact is, when I change the shape of a molecule, I also change its alignment tensor. So I have to be able to account for alignment tensor variations as well. And you can do that by using the steric model that I mentioned Bax developed with Zucteter for nucleic acids. Because the steric model works great. It's called PALES. But not for proteins, because you guys have to, well, for neutral proteins. If they're not charged, you could probably use the same idea. All right.
For the steric, you assume that the molecule never have interaction with the,
Great.
everything is elastic.
Yes, we assume that there isn't any, beyond sterics, there are no other interactions. And the way to ensure that is the case, of course, is how would you make sure the ordering medium is not affecting your sample? How would you do it? How would you make sure, like, what if your ordering medium is interacting with your sample? That would be problematic. I mean, that could be of interest. How would you make sure it's not? So you compare the spectra, and I discovered there are some changes. Well, if there, I'm taking it to a different rabbit hole. So imagine I take the spectrum, and there are differences, but in the chemical shifts. But the truth is, there is no interaction with the medium. Why would there be differences in chemical shifts? I'm giving you a hypothetical. The RNA does not interact with the ordering medium. It's a fact. But that doesn't mean that my chemical shifts are going to be perfect. Why would they not be perfect? What else is not averaging out when I align a sample? We talked about dipole couplings. CSA. So if I partially align an RNA, you will have a incomplete averaging of the CSA interaction. And as a consequence, you'll have a small shift on the order of a few, 0.01 ppm. It's a tiny shift. So you might see a little, so it's not true that you should see no shifts. And so to be super careful and rigorous, what kind of nucleus would you like to compare? One that has a weak CSA anisotropy. Not something with a juicy CSA, because then it's going to have a bigger. What in a nucleic acid has low CSA? What carbon? What part of the nucleic acid has a. Does phosphorus have a big or small CSA? Huge CSA. Forget the phosphorus. Sugar. You guys also have C alpha and C beta, right? Those have small. C alpha aliphatic carbons have small CSAs, so those would be, that's where I would do the comparison. The base carbons, on the other hand, the RCSA contribution can be as big as the RDC. So they have sizable CSAs. But yes, you definitely want to make sure. Now, a lot of crystallographers will come and say, oh, you're adding 20 mg per mil of phage into your sample, and you're having some distortions in your spectrum. Your phage is manipulating your protein or nucleic acid. But I tell people, actually in a cell, what's the concentration of stuff inside a cell? It's like 100 mg per mil. So like when we put 20 mg per mil of phage in our, I argue we're making it more physiological. It's more like a cell. So this neat buffer, you gotta have a clean buffer. Actually, Kurt Woodruff came up to me in a poster when I had bicels and aligning protein when I was a graduate student. Kurt Woodruff came up and he saw these bicels and he looked at me and he goes, those bicels are like jellyfish. I don't like that, because he thought that they were biting the protein. But the reality is that our buffers are extremely artificial, right? And if anything, putting an orderic, like a membrane mimetic or a phage rod, it probably is bringing you a little closer to reality, right? So even if you had chemical shift perturbations, is what I'm saying, I wouldn't freak the hell out, because presumably your sample will also change inside the cell when you incel NMR. All right, thank you everyone. Thanks everyone at Zoom.